Okay, well, we've been considering the problem of a particle in a finite well and trying to find the energies of the bound states for that system. All right? We've progressed so far as to get an equation for those energies, and now we're going to see how we can solve it numerically. Hang on one sec. So just remember, after some work, we found an equation for the energy states, for even parity energy states. And here's the equation. Tangent KL over 2 is equal to alpha over h bar. I'm sorry, alpha over k, excuse me. And what we noticed is that this is actually an equation for the energy because both k and alpha are determined by the energy of the state. So now we have tangent of quantity square root 2me divided by h bar times L over 2. That has to equal square root of u minus e over e. Okay? There we are. So we have an equation for the energy. And all we have to do is to solve this equation to find the energies of the even parity bound states. But the problem we have, or something we'll notice, is that this type of equation can't be solved analytically. We can't rearrange the terms to get energy on one side and everything else on the other side. Okay? So how do we solve it? Well, if we can't solve it analytically, we have to solve it numerically. And here's what that means. What we'll do is we'll put in values for m, l, and u naught, and then we'll make a table of values of the left-hand side of the equation as a function of e. And likewise, we'll make a table of values for the right-hand side as a function of e. And then we'll look for values of e where the left-hand side and the right-hand side are equal. You can probably imagine doing this in Excel or some similar program. Okay? It's perfectly straightforward. Once you've made those tables, it's actually helpful to look for solutions in a graph. Here, let me show you what I mean. All right. So here, what we've done is to select specific values for L, U naught, and M. And then using those values to calculate alpha over k as a function of energy. All right? And then we've plotted that. That's what's plotted in this solid line. That was the right-hand side of our equation. Then on top of that, we're going to plot tangent of KL over 2 as a function of energy. There we are. And now we'll look for specific solutions. So you can see, although we've only plotted a finite number of discrete energies, that there must be a solution between these 2 points, right here. All right? And at that crossing, that identifies a point where the left-hand side of our equation equals the right-hand side of the equation. And so that means that's a solution. All right? So we found an energy state for this problem. Okay? Remember, tangent is a kind of funny function. As you plot tangent of theta, it has poles in it whenever the cosine term goes to 0, so 90 degrees, for example. And so this function, tan KL over 2, has poles too. If we continue it, we have a pole over here, and then beyond that, we get this blue line. And you can see that we have another crossing, another even parity state at higher energy. All right? So now we've identified 2 even parity energy states. Based on what we know from the finite well, we expect that there must be an odd parity state between those 2 even parity states, right? So we should go look for that. Now, to go look for that, we need to go back in our solution and look at the boundary conditions and see how they're different for our odd parity states, and then redo the rest of the calculation. It's actually pretty easy now that we've done everything, but I'm going to leave that to you to do in a problem. In any event, the answer looks like this. We get an additional function, and we look for the crossings of that with alpha over k. and that tells us the energy of the odd parity state. So now we have three states, two even parity states and one odd parity state. And those are the energies for this system. And interestingly, those are the only energies, because those are the only energy states that occur between E equals 0 and E equals 50. And E equals 50 is the top of the well. So we no longer have bound states if we find energy states above the top of the well. But yeah. All right. Okay. Well, now looking back to our graph, we can extract these energies. Here they are. The first state is at about 5.71 eV. The second state is at 22.15 eV. The third is at 45.3 eV. And those are the bound energy states for this system, where finite well, L equals 2, E equals 50, M equals mass of the electron. Notice we only get solutions for this specific problem with these specific values. We don't get a general formula, okay? That's an issue with numeric solutions. But we do get this. All right, well, let's wrap up this problem now. So we've solved the problem of a finite well. We found the bound state energies for a specific well, the one that's shown here, okay? And we illustrated the technique. Our technique here was a very top-down analytical technique, all right? Built for the human brain. You know, we simplify it as much as we can before we start to look for the answers. There are other ways to approach problems like this. One way is to simply numerically integrate Schrodinger's equation for different values of energy and just search and search and search until you find values of the energy where the wave function matches all the boundary conditions. Just brute force. That works perfectly well too, but it's a job for a computer. All right? All right, well, why don't we stop now, and then I'll see you in class.